Okay, so our third speaker is Dr. Amir Pham, professor and Donald and Sarah Munro Chair and Associate Dean from Queen's University. He is going to speak to you today on FRP tensile properties and bond strength to concrete using a biosourced resin wet layup.
Thank you, Sean. Good morning, everyone. I first would like to acknowledge my master's students, Anne McIsaac, who did this work as part of her master's degree. She is, in fact, defending next week. So my talk is about tensile properties and bond strengths, as well as lab splices, actually, of FRPs made of biosourced resins using the wet layup method. And this study is essentially an attempt to shift a bit more towards green and sustainable composites. And we are approaching this topic from the structures and mechanics standpoint and not particularly from the chemistry or material science standpoint. So well-established, well-known conventional resins, primarily epoxy in case of wet layup repairs, are petroleum-based. There have been alternative resins made from other bio-based materials, including epoxidized pine oils or polymerized agricultural byproducts. They have been primarily in other fields, but have not been fully utilized or even fully investigated in the context of structural engineering applications. So examples of the bioresins, they could be derived from corn, sugarcane, soybean, pine oil, linseed oil, and probably other materials. The one thing to note here is that the concept of embodied energy, which is basically the energy required to produce the product all the way until it's a product in our hands to use, is substantially less for all bio-based materials. For example, in the case of linseed oil, epoxidized linseed oil, it's a fraction of that of epoxy in terms of megajoules per kilogram of the material being produced. Another approach is to target the fibers and try to go towards sustainable fibers or bio-based fibers. For example, flax, hemp, and other types of biofibers. The problem is that natural fibers have much lower tensile strengths and mechanical properties, Young's modulus and so forth, compared to our traditional carbon glass fibers. So it is our personal view as a research team at Queen's that if the industry would move towards heavy structural applications, and I'll explain what I mean by heavy structural applications, and we want to go green, then our best bet would be the resin and not the fibers. What I mean by heavy structural applications, I mean retrofitting concrete structures, reinforcing bars and plates and sheets. However, there is a niche for the other fibers in terms of, for example, lightweight sandwich panels with insulated foam cores and FRP skins for aerospace and some lightweight structural applications where we can use the flax or other biofiber skins. So some of the previous work we did on this, we experimented with a type of bioresins which is a fully bio to our knowledge, furfural alcohol, which is extracted from corn cobs and sugar cane. And it showed excellent results, in fact, when used for confining concrete cylinders in terms of the confined strengths and very similar to epoxy-based resins. But please note, this was a contact critical application. When we attempted to use the very same resin in a bond critical application, it was a disappointment. It did not actually bond well to concrete, and there could be something has to do with alkalinity of the concrete surface. Again, that requires further investigation. So we were quite puzzled. The reality is that it turned out that this particular resin, it bonds very well to itself. So when you have a wrapped cylinder, you're having the overlap and it's bonding very well to itself. But to concrete, it was a different story. We were quite ambitious. We thought 100% bio. Okay, that was great, but it didn't work out. So we started looking into other types and perhaps reducing our expectations to partial bio or blends with epoxy as opposed to fully bio. So the objective of this study then is to examine and compare 3 different types of bioresin blends Again, these are available in the market. We did not claim any kind of formulation or chemistry behind this, but they are far from being applied in civil engineering applications. So the first one is a two-part system derived from wood and vegetable byproducts industries. We call it VW for vegetables and wood, and it's a kit. So you don't have much of a choice of the percentage. It is known to be the final product by weight is 41% bio-based product. When I mean bio-based in the context of all this study is agricultural, undervalued byproducts and so forth. The second one is a two-part cashew nut shell liquid. We refer to it CN, that can actually be blended with epoxy. And it has its own curing agent. The third part is linseed oil, epoxidized linseed oil, ELO. Again, this one mixes with epoxy, but it does not have its own curing agent. So the second parameter we looked at is examine the effect of the percentage of bio by weight in the final product. And we varied that for the second and third type from 10 to 40% by weight. Again, we also, the study covered a range from tensile properties to lap splices and also, of course, bond to concrete for both carbon and glass. So this is the test matrix for the tension coupons. We basically had the epoxy compared to the other three types of bio-based resins. For the second and third type, we varied from 20 to 40% bio for CN and 10 to 40% for the ELO. We also looked into carbon and glass, and we had 5 repetitions for the coupons. So we had a total of 90 specimens. So these are the standard ASTM 3039 standard, the typical tension coupons as we know it. So these are the results here. You see here is the epoxy, that's the carbon and glass, that's the epoxy, typical tensile strengths, and that's the WV, which is 41% bio. So these are the percentage of bio. And now that's the second type here, when from 10% bio to 20% to 30%. So clearly within the limitations of this study, it appears that the optimal was 20% in terms of the highest possible tensile strengths. For the epoxidized linseed oil, it was actually interesting. The 10% had higher strengths than the epoxy, but then it drops gradually as you go to 40% bio. For the glass, somewhat similar but not quite the same trend. The last two types did not come all the way up to the level of the epoxy control. So that is the tensile strengths. In terms of the modulus, it essentially no difference. You see the variation within the Young's modulus is higher than the strengths because it's a bit sensitive to the extensometer and so forth to get the Young's modulus and localized damage and so forth. But essentially no major effect on the Young's modulus of the coupons. Same with failure modes. We did not particularly correlate any particular mode of failure of the coupons with the type or percentage. One thing I should mention though is at the higher level of 40% in the second two types, the ELO and CN, the physical examination of the coupon was a little bit flexible. It was not as robust or rigid, if you will, as the lower percentage or the epoxy. And that's a physical sort of examination of the material itself. So then we started moving on towards the lap splice. You will need a lap splice in a variety of applications. For example, when we wrap in columns and so forth. So we used the same. So in this case, actually, it appeared that the WV product was the highest bio that gave us comparable to epoxy. It was the candidate that we felt we should look into here for the splices. So we examined only the WV wood and vegetable byproduct resins. We compared with epoxy, and we varied the overlap splice for using coupons again from 25 millimeter to or 1 inch to 4 inch. Again for carbon and glass, and 5 repetitions. Again, within the limited scope of this study, here is the results. That's the strength versus the lap splice. The horizontal line is what we got from the tensile failure of the coupons in the previous phase. And clearly, again, you increase the capacity, but you don't actually quite get to the full tensile strengths up till 4 inch. Again, the WV product came very close to in terms of the epoxy. In fact, the dotted line here is a tensile of the WV. So I would argue that this is fairly comparable to epoxy. For glass, we had a better luck approaching the full tensile strength of the material for both the epoxy and the WV resins. Again, that's the failure of the splices. Again, bond failure within the interface. We started then moving towards the bond to concrete, which was really that was the primary concern in the first place. Can the material be used to repair concrete or retrofit concrete? And in this case, we actually used the notched beam bond test, which was developed earlier by Gartner and Trey Hamilton and their group, and later been adapted by the ACI 440.9R, and it's part of the testing protocol for bond. I find it actually very useful method, excellent method in that it gives you a quick, simple assessment and comparative between different products. It captured an average bond strength because you would not capture you could simply use the internal forces and get the force and divide the force T by the bond surface area. You get an average bond strength to concrete. So that was the method we used. We covered the exact same parameters as we did for the tension coupons. So the very first table, all kind of 3 types of bioresins and carbon and glass, and we had a total of nearly 60 specimens. Direct to the results. So, well, that's a notched beam that was not even bond. There was no FRP at all here, but that doesn't matter. The epoxy is our reference, in this case here for the carbon, which I call it 0% bio, I guess. And then that's the WV system, came fairly close. And then the CN 10%, 20%, and 30%. So a clear decline from 20 to 30% bio in the CN product. For the ELO, we had from 10, 20, 30, and 40, we had what appears to be a higher strength here than even the epoxy, but I will caution you about this one here. What happens is any specimens that fails by shear in the concrete should be eliminated. So you did not get a bond strength, right? So our average dropped. So there is a bias here because there is a fewer. Oh, I should also mention the repetitions were only 3, not 5 for the bond. So if you remove 1, the other 2 were biased. So I will take this one with cautiously. I would say it's not any less, but I will not say necessarily higher. Again, 30% and 40%, the drop you can see. I will show you the failure modes later. And the same story here happening for the GFRP. But there were slight variations because there was a number of concrete patches, so there were slight variations on FC prime. So we thought we might normalize with respect to the changes in the concrete strengths. So we have the normalized bond strength tau over the square root of FC prime. It changed slightly from the previous slide, just to be more accurate. This shows you again the normalized bond strength versus the percentage bio by weight in the resin. So if that's the control epoxy carbon and glass for bond strength. This is the WV for carbon and glass. This is the CN, and that's the ELO for varying from the 10, 20, 30, and 40, or 20, 30, and 40 for the CN resins. These are the failure modes that you could get from this test. So that's an adhesive failure where failure happened within the resin. We do not see traces of concrete on the surface. And that's a cohesive, and I mean by cohesive here, cohesive within concrete, where it entirely covered by concrete. And then this one is kind of mixed between adhesive and cohesive. And this is the one that failed by shear in the concrete. In other words, not a bond failure at all. And that was eliminated. I think there was only 1 or 2 from those out of the 57. So that's the failure modes. So in fact, the epoxy carbon and epoxy glass were mixed. The WV was cohesive in both. The CN, again, was mixed, and adhesive when you had 40%. The EL, same actually for glass as well, MM and A. For the epoxidized linseed oil, mixed, cohesive, and shear. In fact, one of the repetitions failed by shear, and then adhesive. So the trend is kind of the same as in carbon and glass for each type of resin. So at this point, so the conclusions from this study is that the resin that showed, the resin with the most promising, I guess, with the highest bio content of 41%, and at the same time adequate tensile properties was the resin extracted from wood and vegetable byproducts, and it resulted in tensile properties and models and so forth ranging from -9 to +2% compared to epoxy for glass and carbon. As the percent bio content increased from 20 to 40% in the CN type, and that's the cashew nut based resin, the tensile strength increased until a peak at 30%. So at 30% was the highest value, then reduced when we went to 40% bio. So at that peak of 30%, the results were kind of varied from epoxy from 0 to -14%. ELO resin, that's the epoxidized linseed oil resins, with 20% bio for carbon and 30% for glass, are the highest or the most promising for this type of bioresin, provided adequate tensile properties, and as the percent bio, at this percent bio, the variations from reference epoxy were 0 to -13%. The lab splices, with either epoxy or WV, because that's the only resin we tested for lab splices, reached a maximum anywhere between 75 to 78% of the full tensile capacity within the range of 2 to 4 inches overlap. For GFRP, we reached more, up till 94% or 79% for the two resins, respectively. The WV resin with the highest bio content of 41% resulted in very similar bond strengths to control epoxy for both glass and carbon. And that's bond to concrete. For ELO and CN resins with 20% bio, it resulted in the at least similar bond strengths to epoxy for both glass and carbon. Lower or higher percentage bio affected the bond strengths in a negative way. The other thing is, so bond strength is actually, and we probably know that already, so that's perhaps not a new conclusion, but bond strength is not just dependent on the resin, but actually on the fiber for the same resin. So for glass FRP, the bond strengths were generally lower than that of the carbon by 20 to 29% for the same resin type. Nonetheless, the failure modes were essentially the same. So I think that's it, and happy to take questions.
Neat stuff, Amir. I really like what you're doing with the bioresins. Question that came to mind when you first started in the first one, you said that you had 100% bioresin that worked well in confinement,
yes,
but not so well in bond.
Bond critical, yeah.
Would that resin, would you be able to mix that with an epoxy to create one of your blends?
I never tried, but let me tell you this. Again, with my very limited chemistry knowledge of chemistry background, there are apparently two different classes. The furfural alcohol family is a completely different family from epoxy or epoxidized green resins. So these vegetable or other products are epoxidized, so they are of the same, compatible with epoxy, and you can blend them. I've never tried to mix the furfural alcohol.
Yeah, the reason I was thinking was because you didn't get the good bond, whether you could actually create a primer that was a blend and then use the 100% for the flex, because the more we can go to the 100%,
so this is an open area for surface treatment. We feel the pH has to do with it, but we haven't put our hand on the reason exactly.
All right, well, we'll talk about that one some more.
Sure.
Thanks, Amir.
Thanks, Ars.
I just have a question for the bioepoxy, for the bioproduct. Does it have durability issue, or you have read some literature or other researcher discuss research?
Yes, we did some studies, another student, about epoxidized pine oil, which is not one of those actually. And that was some time ago. And we found it very comparable to epoxy. There was degradation over time. And that was at high temperature in salt solution over close to 1 year. But I believe at that point, the bio was limited. The bio content was probably no more than 20%. We never knew exactly, but it was a lower bio. So the next phase was to do durability on those ones, which we haven't done yet.
Okay, thank you.
I have a couple of questions. How is it to work with these bioresins vis-a-vis epoxy in terms of cure time, gel time, heat that you get from them? Is there any difference? And the other thing is, did you have to do anything to the fabrics in terms of sizing of the FRP itself to work with these?
Excellent. 2 questions there. So the first type was a kit. So we followed the instructions. Right? The 41% WV one, that was a kit. Never used apparently, or to my knowledge, in civil engineering, but it was a kit. And I believe that I don't have exact numbers for the cost, but it was reasonable. But the second ones, we did a lots of trials and errors. So a lots of trials and mixing different percentages. The CN one has its own catalyst, whereas the ELO doesn't have its own catalyst. So we use the catalyst or part B of the epoxy to cure it. But we factored all the percentage normalized to get the total weight of bio. In terms of the fibers, we did not do any sizing. So this was, I'm afraid, it was kind of trial and error shooting in the dark to start with. But there got to be a better scientific approach from the material side in terms of the sizing for the resins.
Right. Thank you.
I mean, for the both types, we know the epoxy, maybe it's for the long-time behavior and durability aspects. Do you have any research on durability of the bio?
Yes, as I mentioned, we did actually durability in the furfural alcohol. Those wrapped cylinders were aged for 1 year, and we did on another type, which is the partially bio but epoxidized pine oil, not linseed oil, which was 20% bio or so, came very close to the epoxy. The furfural alcohol, which were coupons and the cylinders I showed, came a bit weaker than epoxy in terms of tensile strength retention after 1 year. Maybe a bit lower retention by 20 to 30%, 20-25%. There are papers published on this, yes. No, more than 1 year, I'm afraid you have to use the extrapolation functions and there is mathematical models that can go up till 100 years, but yeah.
Now we are moving a little bit away from petroleum products. Do you think there would be a little improved resistance to fire, or?
Yes, I can answer this. For the furfural alcohol, actually. The furfural alcohol, the fully bioresin, is in fact intended apparently in some other applications for high temperature. And we did few years back, we did the TEG, and it came actually extremely promising. So furfural alcohol resin is meant for high temperature applications, perhaps in mechanical engineering and other things.
Just another quick kind of follow-up to Ravi's question. The resins you were using, were the viscosities and stuff and applications similar to what you would do with a standard epoxy resin?
Yes, you mean in terms of the consistency and
consistency
wetting the fabric?
Yeah.
Exactly the same. Exactly the same. Like epoxy.
I am way outside my comfort zone asking this question. But for those alcohol-based ones, for example, derived from corn, if you think holistically about being green, do we really want to be growing more or producing more corn or similar plants to produce this?
Great question, Rudy. Let me clarify a point. They are not extracted from the seeds. The seeds are important. We need them for other things. They are extracted from the corn cobs. So that's, to my knowledge, there is tons of these undervalued byproducts. In Ontario, I was told in Canada, like 10 cents a kilogram. It's a waste. The corn cobs itself, that's the core which doesn't have any other use. Would that answer your question? Yeah. So it's not the seeds.